what you just saw in the previous problem was kind of a little bit of a deep dive into the world of linear programming and how we deal with problems that can be modeled with linear programming. So really when we're dealing with linear programming, as I alluded to earlier, it's trying to optimize something. So usually trying to minimize or maximize some certain type of a quantity. And so that thing that you're trying to maximize or minimize is specified as the objective function. Okay. Now, what we saw earlier was there are some constraints that we want to consider, which you're always going to have in any sort of a business or scientific or whatever sort of a context. Now, those constraints that we saw in the previous problem were actually linear in nature, which is why we're able to call this linear programming, because if you take a look at what we did just previously here, you can see that the graph, the boundaries of all of it, they're all just straight lines because all of the equations that we had for the constraints there were linear in nature. And so those constraints are going to be able to form a region that we call the feasible region that's going to tell you what are going to be all of the possible points that could satisfy all of the constraints, and then from that feasible region, then within that feasible region we can try to determine what's going to maximize or minimize. And what we saw is that if that region is a completely closed shape, then actually both the maximum and minimum actually occur at the corner points of that particular feasible region. So let's just kind of take a look at this in terms of like just a mathematical sort of perspective here. So we have right here, this would be kind of a system of constraints or a system of inequalities that I'm going to go ahead and graph right here. So in the red right there, let's consider that to be x is greater than or equal to 2. So that's like the vertical line x is 2. We can make the line solid, of course, but we'll want to shade to the right of that, so we're above. We'll get to that in just a little bit. And then in the kind of T-list right there, you can see that y has to be somewhere between 3 and 6. And so that would mean that that would be where y equals 3, but then that right there would be where y equals 6. So we're going to have to be somewhere in between those T-list lines. And then finally, we're going to have the fact that x plus y is going to be less than or equal to 10. So that's equivalent to like y is less than or equal to negative x plus 10. So it's like having a y-intercept at 10 and then a slope of negative 1 with that blue line that you're seeing there. All right, so now with all of those constraints kind of graphed, we just need to do the shading. And so the shading is going to require that we go above the red line, between the two teal lines, and then also below the blue line. So it turns out that this sort of trapezoidal shape right here is going to be our feasible region right there. So it does turn out that this feasible region happened to be a closed and bounded region all connected like you're seeing right there, and it ends up having 4 vertices or 4 corner points. And so just kind of what I've iterated already is this vertex principle that says that if there's a maximum or minimum value of a linear objective function, it's going to occur at one or more of the vertices of the feasible region. And so for this feasible region that we found here above, let's find the minimum value and the maximum value of the objective function c equals 2x plus y. So it does turn out that these 4 corner points right here, actually both the minimum and the maximum of that function c is going to occur at the corner points. And so our corner points, let's just kind of list them out here. Let me zoom out just a little bit right here. It looks like we've got a coordinate at 2, 3. We also have a coordinate at 2, 6. Another one at 4, 6, and then a final one at 7, 3. All right, so we just want to evaluate each of these under C. So if we take the first one and we do 2 times x plus y, we end up getting 7. And then if we do 2 times x plus y, there we end up getting 10. And then 2 times x plus y there is going to give us 14. And then finally 2 times x plus y there is going to give us 17. So of those values of c that we found right there, it turns out that right there that's going to be the minimum possible value within the feasible region, and that right there is going to give you the maximum possible value within the particular feasible region.